Audi. Ok. Questo, perché non rompe le balle così.
Poi
Così.
non
ci sarà niente.
Poi
Ah.
Prima sì, però dopo lo provo forse per vedere se il mouse sia scritto.
Good morning, everybody. So we are going to start. The session of today is mostly dedicated to some tools that are quite specific but crucial and extremely useful for running the various detectors that we face in these days and to go to neutrinos and dark matter search, for instance, so the phenomenology that we covered. We start with material screening, so fighting radioactivity. Lecturer is Monica Sisti from INF10 Milano Bicocca. And as for the other lecturer, you have 1 minute to self-introduce yourself.
So good morning, thank you very much. So as Marco said, I come from INF10 Milano Bicocca, and since my start of the career, I worked basically in neutrino physics with a small parenthesis for the PhD in Germany, where I worked on that method. And now I work basically, mostly basically on query double beta decay search, which is going to be upgraded to Qubit. So always for the double beta decay search, but on another isotope, on the 100. And a few years ago, now was almost 8 years, I joined also the Limo collaboration for searching for trying to measure the neutrino mass order. So this is basically my research activity, and at INF10 Milano Bicocca, I have the coordination of the radioactivity lab. So, material screening, that's the topic of today, which is in fact a wide topic that is difficult to cover in just one lecture, but what I would like to try to transmit you today is that material screening is becoming always more and more demanding, and very often this requires a dedicated R&D for reaching the sensitivity that is required for your experiment. So even for screening your material, you have to develop very often a specific technique, very often custom technique, in order to be able to test the materials at the sensitivities that are needed for your experiment. And that's why it is becoming very demanding. So there's no fixed recipe. There are some basic tools that we will introduce today, but what I want to warn you is that it's a continuously developing field. So what we discussed this morning are the sources of radioactive background that we have seen mentioned several times this week as a problem or a tool in neutrino experiments. We will review the strategies for background reductions, and then we will discuss the main techniques for material screening, gamma spectroscopy with high purity germanium detectors, then neutron activation analysis, inorganic mass spectrometry, and alpha spectroscopy. And then I would like to try to show you some custom techniques that of course come from my research experience. So first of all, you all know this, but radioactivity is all around us. So the human being has developed, has grown in a world full of radioactivity from natural radiation, which makes up today about 80% of the annual radiation exposure, for example, in Italy, but it's in developed countries, it's more or less the same situation. And this comes basically for the most part from the radon gas that is daughter from uranium-238, we will see deeply later. From cosmic radiation that is bombarding our Earth constantly, from terrestrial radiation, fossil nuclides, and internal radiation. So also our body has some radioactive nuclide inside, carbon 14, potassium 40. And so this all makes the doses expressed in sievert, which is basically an energy over mass. And this makes most of the radiation we are exposed to every year. And then in countries where medical procedures are, let's say, common screening or curing technique, there's also exposure to artificial radiation, about 20% in Italy. Other sources of artificial radiation are negligible. So why do we care about material screening? Well, this already summarizes you the situation. So everything is radioactive. So we have to take care of the fact that when you increase the mass of your detector, you want to reduce your background, you have to fight with the radioactivity content of each material. So as I told you, I will bring you some examples from my own research experience. So this is the Cuore experiment presently running at Gran Sasso Laboratory. Is an array of almost 1,000 detectors, volumetric detectors, so they work at about 10 millikelvin. And these are tellurium dioxide crystals contain tellurium 130, which is a candidate for double beta decay, neutrinoless double beta decay. So double beta decay is an extremely rare process. It has been observed, the 2 neutrino channel for many isotopes, and with half-lives that are higher than 10 to the 18 years. So it's a very rare process. And the sensitivity to the neutrinoless channel, which is the most interesting one because it would imply many things, but above all that neutrinos are Majorana particles. The sensitivity, as you see, depends very strongly on the mass of your detector and on the background of your experiment. So in this cartoon, you see the development since my supervisor, Professor Fiorini, started this business with tellurium dioxide volumetric detectors in the 90s. So the evolution on the mass of the detector. And so you see summarized in this picture some of the peculiarities. So you have to increase the mass to gain in sensitivity, and you have to reduce background, which very often means reducing, probably you can appreciate in these two pictures, reducing the mass, the mass of materials that are close to your detector. So in the step from Policino to Cuore 0, that was the first hour of Cuore, we try to reduce as much as possible the materials close to the detectors. And so reducing the the materials. Building prototypes, this will be another topic that we will discuss today. And also this has been also discussed a bit yesterday by Barbara, self-shielding of the detector. So that the idea of core is that core means heart, and the heart of this detector should be cleaner than the outer detectors, because the outer detectors make some self-shielding to the inner part. But what is even more interesting in this formula is that if you reduce the background as much as you can, and you reach the background equals 0 regime, then the sensitivity to the neutrinoless channel increases linearly with the mass of your detector and with the measuring time. And this is, of course, very appealing, and this is what all experiments are aiming to. So that's another strong point to reduce background. Another example is Juno. I will go fast here because Barbara has introduced it yesterday. It's a very huge scintillation detector with a mass that is about 70 times the one of Orexino and 20 times the one of Camlan. And here also the radio purity is a strong point, because this detector has the main goal of measuring the neutrino mass ordering. You have seen yesterday the tiny difference between the normal and inverted ordering. And for doing this measurement, we expect, despite the mass of the detector, only 47 events per day. So this means that accidental background must be reduced as much as possible in order to be able to make this measurement. So in the end, what we will see later is that you have to cure the radio purity of all materials surrounding the detector, but the detector itself, which in this case is the scintillator, must also be extremely pure. And these are the minimum requirements for the liquid scintillator of Juno in terms of concentration of natural contaminants, uranium, thorium, smaller than 10 to the minus 15 gram per gram. This is the minimum requirements for solar neutrino. We need to go at least orders of magnitude lower than this number. And potassium 40 is 1 order lower the requirement in the 20 kiloton of liquid scintillator. So I made this picture that is just for illustration. It's not a scale, not a scale at all. But if we take a typical mass of a man that is about 70 kilograms, and you compare it to the mass of Juno, so the man is very small. But when you take the potassium 40 content of a human body, we have about 3 milligram of potassium, which means about 25 milligram of potassium 40, because it has a very low isotopic abundance. This makes about 10 to the minus 7 gram per gram of potassium per gram of body weight for a man. And this is what we are aiming to for Juno. So proportions are completely different. 5 orders of magnitude here, 9 orders of magnitude here. So that's the battle that we have to fight every day. And potassium 40 is ubiquitous. We will see that despite its very low isotopic abundance, it has quite a high, let's say, quite a high importance in the natural radioactivity of our Earth. So sources of radioactivity that are of particular concern for neutrino and dark matter experiments are the natural long-lived radionuclides, uranium, thorium, and potassium 40. Why this? Because they have half-lives that are of the same order of the age of the Earth. So they are present since the Earth formation, and until now they could decay only once, because uranium has 4.5 10 to the 9 years, thorium has about 10 to the 10 years, and potassium-40 is also on the order of 10 to the 9 years. So they could decay only once, so this means their abundance on the Earth's crust is still very high. Then we have the natural medium-lived radionuclides that are almost all daughters of uranium-238. But you can find them alone, separated by from the progenitor, because they, as we will see, they can break the equilibrium in the decay chain. And since radium has quite a long half-life, can form its own decay chain, like lead-210, and as we have seen many times, we can find also polonium-210 in several situations as a single contaminant, especially on surfaces. Then we have gaseous nuclides, radium-222, again, a daughter of uranium-238. We have also a radium daughter in thorium, but its half-life is only 55 seconds. So for this nuclide, it's more difficult to be emanated from materials and to be found alone in the air. You find it, but it's much less abundant than radium-222, which has a half-life of 3.8 days. So it has time to emanate from materials, and it diffuses. Since it's a noble gas, it doesn't interact, so you can find it also very far away from the place where it was emitted. And so it is of concern, of great concern in all experiments. Then we have krypton 85, which is a site of artificial origin, and this is also a problem in for example, for Juno. For example, for Juno. Okay, I try to shout.
Otherwise, we can talk one to
Okay. Then we have the.
Internet, no, aspetta.
No, aspetta.
Arriva.
Sì. Then we have the artificial, man-made, or anthropogenic or man-made radionuclides, which are the result of the nuclear weapon test in the 50s, 60s of the previous century, basically cobalt, cesium, carbon, and then there are the nuclear accidents. We have injected a lot of cesium and strontium in the environment. So these are all coming from, let's say that their abundance, especially of cesium, tritium, and strontium, comes from these, let's say, nice injections of the from humans. Tritium and carbon-14 are also cosmogenically activated continuously in the atmosphere by cosmic rays. So we have them also from natural origin. For example, this is, let's say, the carbon-14 has been used for this reason many times for radiocarbon dating. But now, after this artificial injection of carbon-14 in the atmosphere, it is not possible to use carbon-14 radiodating anymore. And then we have cosmic rays continuously bombarding our atmospheres. So this we will discuss a bit more in detail all these sources. We start from the bottom, so from cosmic rays. Cosmic rays are primarily made of protons, alphas, and heavier nuclei, but mostly protons. And they bombard the atmosphere and then give rise to other particles, neutrons, electrons, neutrinos, protons, muons, pions, and the maximum activity, the maximum production of these secondary particles happens at about 14 kilometers of height. And then the intensity decreases, and basically at sea level we have only muons, neutrons, and electrons. And then to get rid of this, we go underground. And so this is a qualitative picture that shows you how the intensity decreases with the depth of the laboratory. The depth is given here in meter of water equivalent, and it is the usual way to classify the depth. So it's the thickness of water that would give you the same shielding from cosmic rays. So you see that muons decrease quite rapidly, and especially neutrons. The nucleonic component is made basically of neutrons. 95% of them, of the nucleonic component is neutrons, and you see that after about 10 meters of water equivalent, they are almost gone. But this doesn't mean that you don't have neutrons in your experiments, because neutrons are continuously produced by muons, for example, in your shielding. So, for example, lead, that is a common shielding material. When muons interact, they can give rise to showers that contains neutrons. And this background becomes more and more important the deeper you go underground, let's say. And then at a certain point, when the most intense flux are reduced, also neutrons from fission and alpha ion reactions become important. So at the depth of most underground laboratories that you see here, you have to take care about neutrons and muons, basically. This is what remains. Another thing to keep in mind is that the more you go deep, the higher is the energy of the muons that survive. So at sea level, the average energy of muons is 4 GeV, and at Gran Sasso, for example, the average energy is 270 GeV. So here in blue are the European facilities, and in red the extra-European. Here you see Gran Sasso. It's this curve is a qualitative curve in giving the muon flux, but the actual overburden in Gran Sasso is this one, 3,700 meter of water equivalent. And this is, okay, I like this picture because it gives you the distribution of the underground laboratories with their experimental space all over the world. So we said alpha ion reaction. Why this? Because in the underground laboratory you have the rock. The rock contains uranium and thorium, and this gives rise to these reactions and that produce neutrons that then interact with your detector. And you have to take care also of the uranium and thorium contamination in the detector material. For example, in Juno, we have also a source of alpha ion reaction directly in the liquid scintillator because of the presence of carbon-13 that with the uranium and thorium that are even at that low levels that are predicted for the Juno liquid scintillator, they can give rise to some neutrons. Then we said the cosmogenic activated nuclides. We have the natural one, carbon 14 and tritium, but then also all the materials get activated by cosmic rays. And so every material has its own activation products. And so this has to be studied for each experiment individually. The problem is that the prediction of this of the activity, let's say the concentration in the material of the activated nuclides is not so easy to perform because the models are not so reliable, especially the cross section. So you have, if you want to trust the many codes that exist, for example, Activia, Cosmo, that predict the concentration of activated nuclides in the material, usually it's always a good attitude to make an experimental test, for example, at neutron spallation sources, at proton accelerators, where you expose your material and then check, benchmark the prediction of the Monte Carlos. Here is an example taken from this publication from Gerd Deusser and Matthias Laubenstein, where they exposed at sea level in Gran Sasso some copper sheets to see the activation of the copper, which is a material that is used very often as a shielding material, but as you see in our volumetric detector, copper is very pure and it conducts very well, so it is used also in cryogenic detector as let's say holders for the detector material. And you see all the isotopes that get activated in the copper. Some will decay because of half-life of days. Let's say if you wait a few years, they may go away. But cobalt-60, for example, is a problem for the experiments. For example, for Bohr, it's a problem. So you see here. This is a spectrum from Bohr. You see here the two gamma rays of cobalt, which is not the problem. The cobalt-60 has decays with the emission of two gamma rays, one after the other. But the sum of these two is about 2.5 MeV. And that is very close to the expected peak from neutrino-less double beta decay of tellurium 130. So this is of concern, for example, for Bohr. But there are so for every experiment there could be different isotopes that are of concern. For example, Campbell-Zen, that is a double beta decay experiment searching for the double beta decay of xenon, for long suffered from the gamma peak from silver under the metastable because it is very close to the Q value of xenon 136, and this came from the Fukushima accident. So the anthropogenic, in this case, is anthropogenic nuclide. So cobalt-60 may also be anthropogenic, but in this case, it's cosmic activation. And another thing I want to mention is that the very dangerous from the anthropogenic nuclides are the pure beta emitters. So, for example, strontium-90 could be present in the detector material. It's very it's very difficult to detect because it's a pure beta. But if we want to make a precise study of the two neutrino decay, that is this yellow area here for tellurium 130, this goes in competition because it is a beta decay that with an endpoint in this region, so it goes in competition with that. So they could be tedious also for many other reasons. And then finally, the natural radioactivity. So these are the the natural nuclides, uranium, thorium, and potassium. We have said several times, uranium and thorium are the progenitors of two decay chains. It's falling down. Two decay chains with different elements that have different chemical behaviors. And this explains why you can have a break in the decay chain. For example, radium is highly soluble and radon is a gas. So we will see in the next slide better this point. And the potassium 40, we have already mentioned, has a very low natural isotopic abundance, but as you see, despite that, is very common. It's a very common material, nuclide, let's say. So the concentration in the Earth's crust is one order higher than the one of uranium and thorium. So it is of concern in all experiments, and it's also of concern during material screening, because if you don't treat your sample correctly, you may introduce potassium 40 and have it as a result of your screening measurement, but a fake result in the sense that you have introduced it and it's not maybe then in the material itself. So this is one important point of material screening, that the material that you want to screen has to be treated in the correct way, to be sure not to have introduced the contaminants you are looking for. So this is the uranium-238 series. You have seen this probably several times. There are many nuclides decaying alpha or beta. And when they decay beta, they do it on excited states of the neutral nucleus, so they emit gammas, which is very good for us because with gamma screening we can have access here and here to different parts of the decay chain, and so have information about the secular equilibrium. Secular equilibrium, I think you all know what it is. It means that the activity of all nuclides in the chain is the same of the one of the progenitor, and this happens after 5, basically roughly half lifetimes then of the daughter with the longest half-life. So in the case of uranium, secular equilibrium happens roughly 5 times after the half-life of uranium-234 has passed. So it takes 1 million years to go to secular equilibrium. That's why this decay chain is rarely in secular equilibrium, because if you break it, it takes this long time. Depends where you break it. But if you break it here, it takes 1 million years to go back to secular equilibrium. If you break it here, which is radium, the soluble material, then it takes 5 times this half-life. That is only 1,600 years. But it's very difficult to find this chain in secular equilibrium. And this has some implication for material screenings, because as we will see, some techniques, neutron activation analysis, ICP-MS, can only access the information on this, on the progenitor. And so you can for sure reach sensitivities that are higher than gamma spectroscopy, but you will not have information on the lower part of the chain. So you can see, oh, good, but my material has a very low uranium-238 content, but you may have radium, which is quite a typical point of break of the secular equilibrium, and then you have all these negative gamma rays coming from radium that you are blind with some techniques. You cannot access information. Another point of break is radon-222. This is easy to let's say, establish equilibrium after the break here, because this is only 3.8 days. But as we said, radon can go away. And its daughters are radioactive, so positively charged, they attach to the particulate, or they can also, the recoil nucleus can implant on the surface of materials. And then these daughters decay quite fast, but then you arrive to lead-210, which has a half-life of 22 years. So if you have the implantation of lead-210 on the material, you will have forever in your experiment, because it's to disappear, you have to take roughly 5 half-lives. It's 100 years. It's I think far beyond the natural duration of any experiment. And so you will have a constant background from bismuth-210 and polonium-210, mostly on surface. Okay. For thorium, the situation is quite similar to the one of the uranium, apart from the fact that here the decays are much faster than the uranium one. So this decay chain is it's quite easy to find this decay chain in secular equilibrium, because the equilibrium here takes approximately 30 years to be reestablished. And the breakpoints here are radium, so this is the longest living daughter. So if you break here, for example, in a few years, you can get back the equilibrium of the chain. And okay, we have also radon here, but we have already commented that this is its half-life is shorter, so it is less of concern with respect to radon to the. Okay, so we have seen all these background sources, and then we have the problem to design our experiment and to reduce as much as possible the expected background. So now we see the background sources from another point of view, so the point of view of building an experiment and what we have to take care of. So we have to take care of environmental radioactivity, of contamination in the shielding materials. So all the sources that we've seen before can be in the shielding material, in the detector material. We have to take care of radon and its progenies, and we have to take care of cosmic and cosmogenic background. Of course, we have also to keep in mind the different penetration depths of the radiation in the materials. This we will comment also later. So how to reach the optimum background reduction? I propose you to make a case study on gamma spectroscopy measuring device that is small, so it's easy to shield, but gives you already an idea of what one has to take care of. So here we go quite fast. High purity germanium detectors are the best spectrometers for gamma radiation that we have, because of their small band gap. They're semiconductors with a small band gap, so they have a superior energy resolution, and this allows you to recognize the different nuclides in the material. But because of this small band gap, the detector has to be operated at cold, so at the nitrogen temperature, to reduce the leakage current. Here, just for illustration, these are different geometries of the high purity germanium detectors you can find, and depending on the geometry and on the contact depth, thickness, you have sensitivity to different energy ranges and different efficiencies. Usually the configuration of the sample for the measurements is the so-called Marinelli configuration, where you basically surround the end cap of the germanium. And the germanium is, since it has to run cold, it has to be in vacuum, and so it has usually an aluminum cap around. So you put your material all around the detector, or you can put it just on top of it, on top of the end cap. And then you have this well geometry where you can put the sample inside the germanium, so you have a much higher detection efficiency, but of course the samples here are small. So we have to reduce environmental background. So this is a typical environmental gamma field where you have all the gamma rays from uranium, thorium, and potassium. This goes up to 2.6 MeV, which is the highest nitron gamma ray from the Thorium-208 decay, that is a daughter of thorium. So you have to shield, let's say, the gamma radiation field up to 3 MeV. And so with a passive shielding, you have to choose the thickness of your shielding, that is usually a high zinc material, because the attenuation coefficient is stronger. And usually 10 to 15 centimeters of lead are quite a good choice. But we have, as we have said, also the materials contain radioactivity. So if you want a low background detector, you need to select your shielding material. So here you see a table with some shielding material, lead, copper, steel, water, white liquids. But of course, as I said, the germanium detector is quite small, so you can still use lead to make the passive shielding. Also, fluoride, despite its dimension, still has a passive shielding made of lead and copper. But if you have Juno, for example, you cannot think of a lead shielding around. So the only possibility here is to go with liquids. Here you have the attenuation factor of the 2.6 MeV gamma, a comparison for all the materials. And you see the radioactivity content of some samples of this material. I want to highlight Roman lead. Roman lead is a lead that was found on a ship from Roman times that was sunk in close to Sardinia. And this lead is quite appealing because, as we know, we have a lead-210 in lead that has a half-life of 22 years. But Roman lead, of course, is ancient, and so the decay of lead-210 is almost exhausted almost completely this contribution to the background. And this gives me the occasion also to highlight one of the custom techniques that are possible. So to measure the content of lead-210 in this Roman lead, this was measured with a bolometric detector where the absorber was a piece of Roman lead. So it was built a detector made of lead and to measure the radioactivity content, in particular the lead-210 content. Another point that I forgot to mention is that usually, since you can commercially you can find lead that has different levels of lead-210, but in the end you will have also the contribution from lead X-rays in the background of your detector. So usually one makes a lining, so a composite shielding where close to the detectors you have a copper layer that attenuates or shields completely the lead X-rays. So here are some spectra to show you what we are said until now. So this is a shallow lab, only 15 meters of water equivalent. This is a spectrum without passive shielding. This is a spectrum with passive shielding, and this is passive shielding plus moon data. So you can see how the count rate reduces as long as you improve the shielding of your detector. And also underground, this is a Gran Sasso spectra. If you don't shield with your germanium detector, you will still see the environmental radioactivity. So it's quite a high level of background here. But when you put a shielding, this comes from the Heidelberg Moscow experiment that was using germanium to look for the double beta decay of germanium-76, but it's still germanium. With a good shielding, you can reduce the count rate. These are in kilogram per year per kb. So, and then cosmogenic background. So this is a surface laboratory. Even when you have background reduction with lead and copper shields and moon data, you see appearing the neutron activation lines from cosmic neutrons on germanium and on copper. And when you go, this is the 15 meter of water equivalent shallow lab, you still see some lines from the activation from neutrons. How the muon beta works, it's quite easy. Probably you know this. You use typically a plastic scintillator that has this typical spectrum. You put a threshold here to select only the muons, and then you put this scintillator in anti-coincidence with your detector to try to remove as much as possible, depending on the geometry and on the coverage of this veto, the muon background from the detector. And then we have the radon. So radon is present in the atmosphere. In this room, we probably have 20 becquerel per cubic meter. But if you go underground, this is much higher. So if you go in an underground lab, like Gran Sasso, for example, and you don't have a good ventilation system, the concentration of radon can be very high, also higher than 500 becquerel per cubic meter. Can reach also in the Juno lab, it reached also 1000 becquerel per cubic meter before, which is not good for the health also, of course, because you inhale it and you have alpha decays from the daughters of radon in your body. So a good ventilation system is mandatory in underground laboratories to reduce radon, but still for your detector, for your low background measurement may still be a problem because, so you see here the spectrum after few minutes. These are all decay products from radon-222. Then after let's say a few days, these are basically from radon-220, and then some after 20 days, you may still have some peaks, but most of it has gone. And this comes from the decay half-lives of the daughters of radon that we have seen before. So to reduce this radon, you probably appreciate here from this picture, the usual thing is to enclose your detector with a enclosure, usually acrylic or plexiglass, and flush it with nitrogen. With the low radon content in order to remove the radon from your experimental chamber, or pump the sample chamber. So these are the typical measures to reduce radon. And I want to highlight this very nice detector. It was developed by Gerd Oyster in Max Planck for Physik in Heidelberg. And this is a shallow depth, so it is a 15-meter water equivalent laboratory, but with this very complicated but well-studied shielding, and with this hermetic sample chamber that is used to remove the radon, you can compare the count rate in this shallow laboratory with the ones of one of the best detectors in the Gran Sasso underground laboratory. So this is really amazing. If you do a good job with your detector, you can reach very good level of background. So for optimizing a high purity germanium system, we said we have to select materials, but also the design may help you. So if you separate sources of background from your detector, so for example, this is the cooling system of the germanium, and this is the germanium crystal that is protected from the cold electronics by a lead shielding, then you also improve your background. And this is what you have to do usually with your experiment. So optimizing the design is one important part of background reduction. Here I show you the case of Juno. For example, these are Monte Carlo reproduction of Juno components. So this is the stainless steel truss. This is the chimney on top of the acrylic vessel. This is the acrylic vessel with the columns that attach it to the truss. These are the PMTs with all the electronics inside. And so you build the Monte Carlo, the geometry of your experiment, and you put typical contaminations of the material there, and then you build the background budget of your experiment, and you see what you can tolerate at which distance, because of course the most stringent requirements are in the center or close to the detector or on the detector itself. So this is also an important point or part of the background reduction. And then, of course, there is the material selection. Okay, material selection. We have to measure the radioactivity content of the material. We have two ways of doing this. We can measure, we can count the number of nuclides that are inside the material, or we can measure the activity that comes out. So these are two complementary ways. The point is that you have to compare or to know the half-life of the nuclide you are interested in. If this half-life is very long, much longer than your measuring time, then you can perform equally well with a concentration measurement. Equally, maybe with some techniques you go do better than with others, but you can perform both measurement, concentration measurement or activity measurement. But if the half-life of the decay of the nuclide is short, then the concentration measurement is very difficult. So you are forced to measure the activity. So the decision between these two techniques depend on the half-life of the radionuclide, the measuring time, and also the required sensitivity, because if you need a low sensitivity, maybe also a concentration measurement with a short-living nuclide may be done. But here we are dealing with ultra-low background, so it's not our case. So the two numbers that you get from the measurements are related, of course. So here I give you the reported here the specific activities for thorium, uranium, potassium 40, and also of natural potassium, because very often, since for example in ICP-MS, it is measured the element potassium. If you want to compare it, you have to take this number and not this one. This is the specific activity of potassium 40 only. So assuming 1 kilogram of potassium 40. And these are the numbers that relate the mass concentration to the activity. So basically 1 ppb, okay, here there is the legend. So 10 to minus 6 gram per gram is 1 part per million. Then we have 1 part per billion, 1 part per trillion, and 1 part per quadrillion, 10 to minus 15 gram per gram. So 1 ppb, 1 part per trillion is about 4 millibecquerel per kilogram. In thorium, it's about 12 millibecquerel per kilogram in uranium, and about 265 millibecquerel per kilogram for potassium 40. So these are the numbers. So going back to our decay chains, if we have secular equilibrium, this means that the concentration of the nuclides that have a shorter half-life is much smaller than the one of the progenitor. That's why it's very difficult to make a concentration measurement. So these circles, when they are orange, it means the best measurement with, for example, ICP-MS, and yellow means very difficult measurements that can still be done, but with very special measurements and are not straightforward. While here are the gamma emitters. I've put in yellow these gamma emitters in the uranium, the upper part of the uranium chain, because they are difficult to be detected since their branching ratio is very small. So it's very good when we see the 1 MeV emission from protoactinium 2034 metastadium, but it's not so easy. So this is a table that more or less gives you the sensitivities that you can reach with the different techniques. So these are the ones we will discuss in a few minutes. I want to highlight one point, alpha spectroscopy. So you may ask why, since all the decay chains, the natural decay chains have many alpha decays, why don't we do alpha spectroscopy? Well, alphas, as you know, travel very little in the materials. So with alpha spectroscopy, you can access information only on the surface. So if you want to have information on the bulk of the material, you have to use radiation that is traveling in the material and getting out like gamma emitters. So alpha spectroscopy is good for the surface of the materials. Neutron activation analysis and mass spectrometry are techniques that assess information on the bulk of the material. So the techniques, so we will go now through these techniques. The first one is gamma spectroscopy. We have said several times, I will repeat again, that it's the only technique that
Yeah, we are at about half time. So do you think it's the proper time for questions on the first?
When they want, they can stop me. Yes.
That's right. On the previous slide, I wasn't quite, I didn't quite follow why are the ones in yellow?
The ones in yellow are because it's more difficult to detect. So these gamma decays, if you go back to the slides where the branching ratio of the gamma decays is given, the branching ratio of these two decays is very small. It's very small, so it's difficult to see the gamma line in the spectrum. So you have to the protoactinium is a problem only of branching ratio. For thorium, It's a problem also of energy because it's a 90 kV, so it is in the low energy part of the germanium spectrum where usually the background is higher. So these two look lights are difficult to be detected, both because of the branching ratio and the energy of the decay. That's why they are in yellow. But with good germanium detectors, you can detect this light, if they are present, of course.
Yeah, similar for lead-210, right?
Similar for lead-210, yes, sorry, I didn't mention because the lead-210 has the gamma line at 46 kV, which is very low. So also this is very difficult to detect. And that's why it's difficult to assess the lead content, lead-210 content of the material.
So what would you use to screen the lead shielding to the germanium detectors?
Yes, usually, yes, you use a germanium detector to shield them, and you do the best that you can.
No, but what would you use to measure the length of like the background of the shielding?
Yeah,
Oh, you would use the.
Yes, yes.
Oh, okay.
A well-optimized germanium detector. If you need lead for another experiment, what we do, for example, in Gran Sasso, this Stella facility that probably I didn't mention before, there was a picture of the Stella facility is in the Gran Sasso underground laboratory. This is a facility that is there to help experiment to screen materials. And usually, when we had to build a pore, for example, we gave them no, it doesn't work. Okay. We gave them, for example, this is, for example, the copper for the experiment, or you can give the copper for the shielding or the lead for the shielding. And you measure it by gamma spectroscopy. If you're not satisfied, you can think of your custom technique to screen the material to have a higher sensitivity. But the basic, if you have for shielding, for example, you usually can have huge masses. It's easy to collect. So gamma spectroscopy is still a very good choice.
Thank you.
Please.
Yes.
It's a good question. Maybe you mentioned data, but you mentioned the background budget. And specifically, I was wondering for something like a liquid scintillator experiment at Juno, where does most of the budget come from?
For example, it comes from everything. The liquid scintillator first, then the materials that are close. So the liquid scintillator is inside the acrylic vessel. So we have stringent requirements for the acrylic vessel that contains the liquid scintillator. But the glass of the PMTs is usually the glass is quite dirty. And the glass of the PMTs that are reading the light is also of great concern. That's why if you remember the picture, there is at least 1.5 meters of water between the PMTs and the acrylic vessel. This is to shield the background of the PMTs, which are probably one of the most serious sources there.
So nothing with metal. I was wondering if there's any background coming from a metal surface or something.
Metal, yes, the truss is of metal, but this is much less important than the truss is not that important, but the acrylic vessel is kept from by columns that are attached to the acrylic, and the cobalt-60 in these columns could be a problem. That's why this stainless steel is of higher quality, of lower radioactivity content with respect to the complete truss.
Okay, could you tell me a little bit how much into the magnitude, how much it would be in the total budget? Like, is it like 1% or?
I will tell you later because I don't know. This was done some time ago. But in the end, in the Juno budget, what remains mostly is the background from the closed components. So the acrylic, which is now very low, and the liquid scintillator. This will dominate. So we have done the design and the choice of the materials in a way to have the lowest possible contribution. Then if you want to have the exact number, I will tell you.
I was just wondering, but I guess it's very common.
Yes, there we have a publication on that where you have all the numbers there of the budget. Of course, then we will see what will come from the experiment.
There's another question.
Sorry.
So you would, so when you use high purity germanium to do the gamma spectroscopy for all the background events, how do you deal with quantum scattering? Because
How do you, sorry?
deal with the quantum scattering of all of these gamma. Is there a quantum suppressor around the high purity germanium?
Quantum scanning.
No, in the Gran Sasso detectors, there's no problem of that because the background is very low. Then the quantum scattering doesn't give you an important contribution. You don't have so many peaks there.
But do you mean the quantum scattering of the background or from the gamma ray of the material to be screened?
Yeah, from the gamma ray, the material to be screened.
So,
Ah.
absorption or you call it full absorption?
For this, usually it's a full absorption. You have I mean, it can, of course, you are right. If you have a strong contamination in the material, then you see the full peak. So you can say which is the contaminant of your material, and then you have the quantum tail that will cover possible smaller contaminations that are inside the material. This is of course a problem. So this is is a limitation of the sensitivity, of course, because if you have a strong high energy contamination, this will cover the low background part. Yes, this is true. Then you can only give upper limits. So what you usually do, you have all the contaminations. So look at this, for example, you have, here are all upper limits because this was clean, but in case you have a dirty part, you give the contamination of that nuclide, and then for the others, you at lower energy, you will give upper limits. The probably will be bad because there is the quantum background that is given by the material itself. Okay. So gamma spectroscopy, we have talked a lot about this. I just want to show you a couple of very nice measurements that have been performed in Gran Sasso. This is of a Juno acrylic sample. Of course, Juno is not in Gran Sasso, and so this was a favor that Matthias has made to me to make these measurements. 14 kilograms of acrylic, of the Juno acrylic, and these are the results of the measurement. These are all upper limits, but you see that it could reach a very good sensitivity. This is another example from the Cuore experiment. This is the copper. We use in Cuore two types of copper. One that is a cryogenic copper, that is not this one, and this one is okay, it works also very good at cryogenic temperatures, but it is for the shielding of the copper, yes, thermal shielding of the cryostat. This was with less than 8 kilograms. And what I find interesting in this measurement are all the cosmogenic activation of the copper that you can see here. So cobalt 60 was only an upper limit, but you see cobalt 57, 58, and manganese 54. By the way, manganese 54 was present at the beginning at the start of the measurement of Cuore in our spectrum and was coming from copper. This is very quickly, just want to show you if you have, if you don't have a low background, sorry, an underground laboratory, but a laboratory at sea level like we have in Bicocca, you try to reduce the background with all possible ways. And for example, we have this measuring system with two gamma spectrometers, so germanium detectors that are facing one another, and you put the sample in between, and by using the anti-coincidence, you can reach quite good sensitivities. Of course, are not comparable with the Gran Sasso one, but still good ones. And we have another detector that is used for beta gamma coincidence measurements, and these are the minimum detectable activities that for this system, and I will explain you why we developed this detector in a few minutes. So these are the pros and cons of germanium spectroscopy. So it's a non-destructive analysis. You don't need to prepare the samples, which is also an advantage, because as we will see in ICP-MS, for example, this is a very critical point. It is sensitive to equilibrium breaking on the decay chains, and it has very good detection sensitivities when the system is properly optimized. The cons are that disadvantages are that you need very huge sample masses for achieving high sensitivity, which is easy. For example, if you have copper or lead shielding, you can have a huge quantity of materials. But if you, for example, want to check some electronic components, if you have to put together 1 kilogram of electronic components, first of all, it's quite expensive. And second, you have to buy all this material and then discover that it's not good, you have to throw it away. So it's not always the best solution. Measuring times are long, because for high sensitivity, I didn't probably highlight the measuring time here. This was 37 days, and here was 27 days. So it is, for good sensitivities, you need several weeks of measuring time. It's only sensitive to gamma emitters, and then, okay, for you have to accurately evaluate the efficiency of the system, so you need the Monte Carlo simulation for every geometry that you measure in your detector. Then we come to neutron activation analysis. This is a nice technique that gives you information, sensitive method for qualitative and quantitative determination of the elements inside the material. And the idea is very simple. What you do is if you have an element that is stable or has a very long half-life, so a very low activity, then you transform it in another nuclide that is artificial, but that decays fast, and so you can achieve a higher sensitivity for your measurement. So it's just very quickly how it works. You bombard with neutron your target. You form a compound nucleus that usually de-excites quite fast. And then it becomes, it has an extra neutron, and to return to the stability valley of the nuclides, it goes through a beta decay, usually or hopefully in this case to an excited state of the neutron nucleus, in order for us to detect the gamma rays. So basically you activate at the material with neutrons, and then you measure the decay gamma radiation. So this is the prompt radiation that is emitted in 10 to the minus 12 seconds. So if you want to make a test with this emission, you have to have a detector inside the nuclear reactor, for example. So this is not the usual way to go. And this is what is also called the delayed gamma neutron activation analysis, that is to detect this gamma from the beta decay of the activated nuclides. So the most you can use for neutron activation some neutron sources, which have specific energies, but the most convenient way, of course, is to use a nuclear reactor. where you have a strong source of thermal neutrons, for which the cross section for neutron capture is highest. So this is a nice picture of the Cherenkov radiation from the trigger reactor in Pavia that we use for the neutron activation analysis. So the key ingredients is that you have to use a high neutron flux for an isotope or an implied that has a high enough neutron capture cross section. And then you need to have a convenient daughter nucleus. What does it mean? It means that it has to have a half-life that is not too short and not too long, otherwise it makes no sense to make all this business. And that the gamma emission happens in a region of the energy spectrum where the background of your gamma spectrometer is not too high. And the sensitivity depends on the type of material, on the neutron exposure time, on interferences in the matrix. So this is very important because if you want, for example, to study the uranium and thorium content in copper, the copper is a metal, it activates a lot, and you cannot take out of the reactor this your sample before 1 month, for example, and then many of the measurements that are useful for you cannot be done. And then, okay, this also the radio purity of the sample container is important because you can, so everything is bombarded with neutrons. If you have a dirty container, this can transmit some of the its radioactivity to your sample. So this is the timing of a neutron activation analysis measurement. You have an irradiation time where you build up the activity. Then you take out your sample from the reactor. The nuclide that you activated decays in this waiting time. That is usually the time needed to extract the sample, to check it for radio protection, and then to bring it to your lab for the measurement. And then it continues to decay while you measure. And of course, you measure this decay to assess the number of isotopes that are contained in your sample. We do neutron activation analysis mostly for potassium 40, thorium 232, and uranium 238. Of course, these are the most dangerous contaminants. So this is how it works. For potassium, of course, if you want to make the neutron activation of potassium 40, you end up in potassium 41, which is stable, so it makes is no help. But potassium 41 gets also activated by neutrons, and in potassium 42 that decays in 12 hours. So to have a good sensitivity for this, it is a quite nice measurement to be done with neutron activation. It's quite fast. In a couple of days, you have an answer on the potassium 40 content of your sample. For uranium 238, this is the decay, the chain of reactions, and you end up with neptunium 239, which has a nice feature that I want to highlight, that this gamma, so these are all the gammas that are emitted from neptunium 239, and usually these ones and these two are the ones that are used for neutron activation, but in particular this one is a metastable state, quite fast. It's 190 nanoseconds, and so you can use, and we use this to reduce a lot the background using a triple coincidence. So the beta, the beta minus, plus this gamma or electron decay, this electron or beta decay, and then the other gammas. So this is quite convenient, but you can use just this one to assess the uranium-238 content. And for thorium-232, we used the protactinium-233. The problem with this, you see here, it's 27 days half-life. So to reach a good sensitivity, this is in one sense is good because you have all the fast decaying interference that go away when you measure when it's the good time for measuring thorium activation. But on the other hand, to have a response, you need almost 1 month, and this is yes.
Why don't we use accelerators for neutron activation?
Accelerators to accelerate what?
Protons into lithium-7 target, then we get a neutron cone with a specific energy.
Yeah, this could be another type of activation. Usually, this is not used, as far as I know, for material screening. This is much easier and you don't. So at research reactor, you don't. You have high fluxes, but not that high that can destroy your material, because this is also a problem that you can have.
Monica, can I ask you a question?
Yes.
Maybe if you go back to potassium 42, can
Yes.
you spend a few minutes to help us, to guide us how to read properly this kind of table? Because I think that most of us struggled many times in this table of isotope kind of
Yes,
table.
so
There are
you
a lot of numbers, and not all of them are immediately clear.
Yes, so you have the branching ratio of the decay here and the energy. So this is the most important information you have to get. And for potassium, for example, this is very important because you see, I didn't mention, so thank you for the question. This has a 1.5 MeV of decay energy, and this is very also why neutron activation for potassium is very nice, because at 1.5 MeV, usually the background of the germanium spectrometer is very low. So apart from the interference that comes from sodium 24, which is quite typical, but apart from that interference, it's very clean, the spectrum in that region. So you can access very high sensitivities here. So you have all the decay levels here and the branching ratio. So you check what is the most convenient energy.
So in this case, the branching ratio
is 18%,
which means 18%.
18%. Yeah.
And that's the branching ratio of that gamma.
Of that gamma. Yes.
Not of the level, which is on the left, right?
Yes, but yeah, it is the level, 18%.
Yeah, but I mean, in this case, it's the same because.
Yes, in this case, it's the same.
But
Yes.
if it goes into
another,
state,
yes, you have to read here the branching ratio of the specific gamma.
Okay, thanks. And when I mean we care, I don't include you people. High energy neutrinos doesn't care of this, but we care.
Okay, so very briefly, this is the activation rate formula and how from your measurement, so this is what you measure with your gamma spectrometer, you calculate the activation rate with this formula, and then you can go back to calculate the number of precursor of the nuclide of interest that are present in your detector. Of course, you need to know the flux of the neutrons and the cross section, which are not usually known very precisely. So usually for neutron activation, you aggregate some standards together with the sample containing the same nuclides you're looking for, and then from those standards you get these numbers for every irradiation campaign. So this is a picture of the trigger reactor in Pavia. This is the core of the reactor. This is usually the channel, the rotatory channel that we use for the irradiation of the samples. And this is, for example, contaminant concentration that we measured in an acrylic sample of 6 grams that you see here. And these are the results that we obtained for potassium, uranium, and thorium. So we can easily access the sub-PPT sensitivities. This is another sample for the liquid scintillator of Juno. And this was done with a beta gamma detector. But you see here, we are quite below the sensitivity that is needed for Juno, 10 to minus 15. I mean, with a laboratory sample that is very small, it's very difficult to get to these very high sensitivities. And the main limits are the sample mass that is limited and the presence of interferences. So to reduce the background, as I mentioned, we use this beta gamma coincidence detector, beta gamma, because when you make a neutron activation, the nuclides are beta unstable, and you can, so with a scintillator, you detect the beta that decays and the gamma cascade that comes after with a germanium detector that is placed below. And this gives already some strong background reduction from the environmental background. We have also Vito around. And then to reduce the interferences, there is this technique of extraction chromatography. There are some resins that have chemical affinities with some specific nuclides, so you have to find the resin that works with your nuclides. The one we use have good affinities with uranium, thorium, neptunium, and protactinium, and this selects, with some efficiency of course, the nuclides you want to measure in your sample. The nice thing with neutron activation is that if you do this after the irradiation, when you have artificial nuclides, you have no risk of contaminating the sample using these resins. While for example, for ICP-MS, where you are forced to use this technique before inserting the sample in the detector, this is a big problem. So this is, I don't want to spend too much time, the recipe that we have developed at Milano Bicocca. So this, to go back to the point of developing your custom technique to assess the sensitivity that you require. So it's a neutron activation with some pre-treatments and post-irradiation treatments and beta gamma screening to increase the sensitivity that, as I showed you in the table before, was limited by the sample mass limitation. And here we pre-concentrate the sample before the irradiation, so we artificially increase the mass. The mass that goes in the reactor is always the same, but it's concentrated. And after all this, this is the sensitivities we could reach until now. Here we still have some limiting factors that we are trying to cure. So, but we are in the range required by the Juno experiment. So this is the typical sensitivity you can reach with neutron activation analysis at the level of PPT with simple activation and gamma spectroscopy. With a coincidence, beta gamma coincidence, you can go to 10 to minus 13, 10 to minus 14, and then if you use also radiochemical treatments, you can decrease of another order of magnitude. So pros and cons of neutron activation analysis is, I said, has a high sensitivity. In principle, it's non-destructive. This depends because the flux of neutrons, if you expose your material for a long time, for example, the acrylic is transparent when you put it in the reactor. When it comes out, it's yellow. So it's non-destructive. You still have the sample, but it's not as nice as before. After the neutron irradiation, the samples can be manipulated without the risk of contaminants, and you need small samples, so you don't need huge masses like in the germanium spectroscopy. The drawbacks are that it's only sensitive to decay chain progenitors, as we said already. It's not effective for all elements, and the measuring times are long. For uranium, you need at least 1 to 2 weeks and up to 4 weeks for thorium. So it's not as fast as ICP-MS. ICP-MS is another technique which is very, gives impressive results. There are many types of ion sources, different types of ion separators. So the idea is that you introduce a sample in your material. This gets ionized by the ion source. And then you have a way to separate the ions and measure the mass over charge ratio with a detector that is put at the end of the detector, yes. And it's important that you measure the mass over charge ratio, because this is one of the problems of ICP-MS. If you have ions that are doubly charged with a high mass, they are, so for example, if you have a mass 150 doubly ionized, for the detector, it is like a mass that is 75. So you can have misinterpretations because of interferences that are different ionization stages and different compounds that can form inside the ion source and then are not correctly filtered by the ion separation. So usually the sample that you have to introduce is liquid, so you have to treat the sample before in order to for this to become a liquid. It gets nebulized inside the spray chambers, and it gets mixed with argon. You get a sort of aerosol that is then inserted in the torch. Here you see the torch that reaches a very high temperature. So this is ICP-MS with the plasma, with the argon plasma source. And this reaches a very high temperature, and this plasma is capable to ionize almost all chemical elements. That's why it is very powerful. And then with some lenses, you introduce it in the ion separation part of the detector. Here is a table with all measurable elements of ICP-MS. The nice features of ICP-MS is that with the same in the same measurement, you can span from ppm to ppt and with several elements in the table of elements. So it is very powerful and very nice to get information about the composition of your sample. So this is how basically the separation works. We can go very fast here with the magnetic field. You can separate the ions according to their mass. And the simplest, so this is the simplest separation that you can have with just a magnetic sector. There is this quadruple ICP-MS, which was used a lot in the past, and now, as I will show in the next slide, very recent developments. Here, basically, you have 4 hyperbolic rods and with some electromagnetic field that is constantly changed in order to let only the ions with the mass that you want pass through the rods, so in the middle of the rods, without touching them. When they touch the rods, they get out of the stream and they don't reach the detector. So this is a way by adjusting the electromagnetic field to separate the ions or the specific mass to charge ratio. So it's a filter of mass to charge ratios. These can suffer from many interferences. So recently there have been added some helium gas collision cells to remove polyatomic ions. And now the latest the latest release is the triple quadruple. In Gran Sasso, this machine is being installed in these days, and this can reach very high sensitivities. I said that you can have a magnetic sector, but to improve the ion separation, if you add an electrostatic sector that makes only a filtering of the energies, you can improve a lot the separation, because it doesn't select, the electrostatic sector doesn't select according to the mass, it selects according to the energy. But of course, the bigger is the molecule, or the slower is its so the kinetic energy depends on its mass and on its velocity. So if you select the energy, you can select or remove polyatomic atoms from your stream. So this is the double focusing ICP-MS. So you have the source and the injection, and then you have the magnetic analyzer and the electrostatic analyzer, and this gives a very high sensitivity, high mass resolution. This is one of these machines at LNGS. So this is a nice picture from Stefano Nisi, the head of the chemical services at Gran Sasso. So what you need for a good ICP-MS measurement is, of course, a good instrumentation, but the basis of this pyramid is that you need to have to be able to do clean chemistry. You have to work in a clean room. You have to use acids and containers that are clean, and you have then to make a clean preparation of your samples. Otherwise, if you introduce artificially contamination during the sample preparation, this may be a big problem. So these are some results measured at Gran Sasso, for example, on copper. So this is the detection limit, and this is the measurement of contaminants in a copper sample. Of course, this was solid, so it had to be dissolved in acid and prepared properly for the measurement. This is a Roman lead sample, again at PPT sensitivities. And this is the contamination on a Teflon sample. Teflon is also a very clean material that is used in Lobel experiment. I want to highlight only that for thorium and uranium we have PPT units, but for potassium we have BPD units, because ICP-MS is not a good sensitivity for potassium, because the plasma is made with argon. Argon forms a polyatomic species with hydrogen. Argon 38 plus hydrogen makes 39. Potassium is 39, the main, and so the sensitivity of ICP-MS for potassium is usually not so high as the thorium and uranium ones. This is a recent development that is interesting for solid samples. So instead of injecting the sample in a liquid form, you use a laser ablation to remove parts of your sample and insert it in the machine. And this is nice because you can screen different parts of a surface of a sample, for example. With some colleagues of mine in Bordeaux have used this for the acrylic sample of Juno to test the surfaces in several points, and with several scans you can also go deep in the material and see how the contaminant moves with depth. The drawback of this is that, of course, first of all, surface impurities are never uniform in the surface of the sample. So if you scan in one point, you may have a different result in another point. But the bottleneck of this method is that you don't have a clear way to quantify to give an absolute quantification of the contamination level. But of course, this is very interesting and can be developed further. So with ICP-MS, you have a very good sensitivity, PPT or even lower. The analysis is very fast. I didn't mention, but these measurements require a few hours. So this is very convenient. You need small sample masses. So if you have small samples, this can be a solution. You have a wide dynamic range of multi-element detection, so you can measure several elements and with different contamination concentration levels inside the material. It's a destructive analysis because you need the sample to be liquid, to be inserted. You have many interferences and matrix effects, so you have to really know chemistry very well to do these measurements, and you have low sensitivity for potassium 40. So run out of time, so I try to be faster because I want to give you some highlights of the custom techniques. So what we have seen up to now, we have, I hope I have convinced you that material screening is highly challenging. We have gamma spectroscopy and neutron activation analysis in the ICP-MS. This is sensitive to the entire decay chains, while these techniques focus mostly on the decay chain progenitors, so these are complementary. But this is not the end of the story. So once you have found the material that you like, you have to take still some methods, because if you have measured one sample, you have to be sure that the producer of this sample gives you the same batch for your experiment. The entire production comes from the same batch that you have measured, because different batches may have different contamination levels. You have to take into account that you have to machine your sample, then your machining usually introduces contaminations. And also the storage conditions are important, because you may have radon implantations, and also if you are in a dirty environment, this can contaminate your sample. And the surface is never as clean as the bulk. Please keep in mind, whatever you do, if the bulk is clean, then you treat the surface, and this will have a completely different contamination level with respect to the bulk. So you see what alpha can cause. This is a spectrum of the ball experiment. So we did, of course, we screened copper in every possible way, and we cleaned the surface with a special custom-made procedure. But still, you see a lot of alpha lines in our spectrum. This is where we expected the double beta decay peak, and the tails from the alphas produce background also in this region, that is gamma region. You need, so this is a warning, you need to take into account the surface contaminations may be your limitation point. In QPID, we will cure this with active alpha discrimination from the detectors themselves. So to make alpha spectroscopy, unfortunately, there are not many ways. You can use silicon barrier detectors. These are small chambers. This is in our lab in Bicocca. You can measure samples of this size, about 5 centimeters. And at the surface laboratory, you can reach typical sensitivities of microbecquerel per square centimeters. We measure in times of 30 days. You can do probably better with this detector that you can buy. You can check it at this website, and I found this in this conference presentations that you can reach for polonium-210, for example, nanobecquerel, tens of nanobecquerel per square centimeter sensitivity with a measuring times of about 80 days. And then this is a late detector. It's not existing anymore, unfortunately. It was dismounted last year. I think it was in Canfranc. It is the WIPO detector. This was a very nice detector to measure alpha contamination of very thin samples. This was put in place to measure the sources for the NEMO double beta decay experiment. So with tin foils of the size up to 3.5 square meters, so much bigger than the measuring space that we have seen for the previous two detectors. And by using the BIPO decays in the chain, so alpha and beta coincidences, they could reach 0.1 nanobecquerel per square centimeter of sensitivities for uranium and thorium surface contamination. So this was the best detector available for alpha spectroscopy. But if all this is not enough, if this is not enough, what you have to do? Then you have to build your custom detector. So there's no other way, because the techniques we have discussed so far are the most sensitive available on the market. And so if they don't reach the required sensitivity and you need to test, to check it before putting your experiment at work, then you have to think of your way of checking. So, for example, this comes from the Pole experience. So we had this, we call them CCVR, Pole Crystal Validation Run. And so during the mass production of the tellurium dioxide crystals from the Chinese producer, we were receiving the detectors. These are almost 1,000 detectors in Pole, and we were receiving them in batches, of course. And we were taking some samples and measured them like if they were in the final detector, so in the same mounting system, and in a dedicated cryostat to measure the surface radioactivity and the bulk radioactivity of the crystal. So this is one example. But then, of course, in 1 month or 2 months or even 3 months, with a small setup, you cannot reach the sensitivity you will have with your final detector. So the other possibility is to build a prototype. And this is done by many experiments, usually. So you build a smaller detector to check that everything that you have put into place to reach your background level is achieved. And so this was the first Pole tower that we measured in one of our older cryostat, another Pole one. And then we measured for more than 1 year. And we built the background model on the data. So this is not anymore a budget, this is a model. And we could devise the bulk and surface. Okay, there is not important to read the numbers, but it's just to show you that for every part of the experimental setup, we devised and calculated the bulk and surface contamination and to confirm the budget that we had produced for water. So I'm done. There are many other topics we didn't have time to mention, but just wanted to give you the idea of how difficulties can be.
We thank Monica.
Was very nice, wide, and at the same time, deep overview. Questions? Please.
What are the advantages of using an XIA alpha counter over other types of screening equipment?
Sorry, say it again.
What are the advantages of using the XIA alpha counters over other types of?
Because this one, you can put wider samples. And the sensitivity, so this you reach microbecquerel, and this is also surface laboratory, so without too much work on it, and you can reach tens of nanobecquerels per square centimeter if properly done the measurement. So, and with bigger samples, which is also quite important.
Other questions? Please.
Why specifically polonium-210?
Because as we saw before, polonium-210 is the usual contamination that you find on surfaces. You cannot measure by alpha the lead-210, and polonium is its daughter. So when you have lead-210 implantation, you end up with polonium. And so you measure polonium, and you have, if it's in equilibrium, you have also an indication of the lead.
I meant, why not polonium-214, which produces the highest energy alpha?
Lead-214, you mean?
No, polonium.
Polonium-214? Yes, but this is upper before the lead-210. And so you don't.
But not secular equilibrium.
It's difficult because if you have a radon contamination, a radon plate out on your sample, then all these decays are quite fast, and you end up with the lead-210. You will have only lead-210 there. And so you measure the polonium by alpha spectroscopy.
Any other question? So if not, we thank Monica. And before going to the think just I think this I think this can be the perfect soundtrack for this. All of us, no matter what.
My son has chosen this.
Exactly. So coffee break. In half an hour of coffee break, 20 past 11 back here. Sì.
Thank you.